All right, let's jump right in. Today, we're going to tackle one of the most elegant concepts in all of graph theory: maximum flow and minimum cut. Now, this is a huge deal in network analysis. It's used to optimize everything from internet traffic to supply chains. And by the end of this, you'll see exactly how it unlocks solutions to a whole bunch of really tough problems. So, we're going to start with a puzzle. We'll look at two problems that seem totally different at first glance. But, as you're about to see, they share this surprising, deep connection. Okay, on one hand, you've got the maximum flow problem. Just imagine this network is a bunch of water pipes. The source is where the water comes in, the sink is where it goes out, and every pipe has a max capacity, right? The question is, what's the absolute most water we can push through this thing, from source to sink? In this example, you could maybe send 4 units on that top path, 3 on the bottom, for a total of 7. And it turns out that's the limit. Now, on the other hand, we have this thing called the minimum cut problem. Think of this like finding the cheapest way to sabotage the network. Which pipes could you cut to completely stop the flow, where the cost is just the sum of their capacities? Well, if you look for the weakest link, you'll find that cutting those 2 pipes in the middle, with capacities 4 and 3, does the trick. And the total capacity of that cut? It's also 7. So is that just a coincidence? No way. The fact that the maximum flow is exactly equal to the minimum cut is the big idea we're going to unpack here. And to really understand why this is always true, we have to look at the engine that actually calculates the flow, the Ford-Fulkerson algorithm. So how do we actually find this maximum flow? Well, the classic method is called the Ford-Fulkerson algorithm, and it's basically this iterative process that just cleverly builds up the flow, piece by piece, until you just can't add any more. You know, the idea at its core is surprisingly simple. You start with zero flow, nothing. You find any path from the start to the finish that can still carry some flow. We call that an augmenting path. And you push as much as that path can handle. And then you just do it again. You keep finding paths and pushing more flow until you literally can't find any more paths. But here's the real genius of the algorithm. This is the secret sauce. Its power comes from this concept called a residual graph. It doesn't just track how much capacity is left. For every bit of flow you push forward, say from node U to V, it creates capacity on a reverse edge going from V back to U. And this is so important because it lets the algorithm fix its mistakes. It can undo a choice it made earlier by pushing flow backward, which can free up capacity to find an even better route later on. It's incredibly clever. So the whole process really just boils down to this simple loop. First, find a path from the source to the sink where every edge still has some gas in the tank. A simple search like BFS is perfect for this. Second, find the bottleneck on that path. That's just the edge with the smallest leftover capacity. Third, add that bottleneck amount to your total flow. And fourth, update your residual graph. You subtract that flow from the forward edges and you add it to the reverse edges. Then you just go right back to step 1 and do it all over again. And this gives us a really clean way to know when we're finished. You know you're done when you literally can't find any more paths from the source to the sink in that residual graph. They're totally cut off from each other. At that point, the total flow you've built up is guaranteed the maximum flow possible. Okay, so now we can finally solve that puzzle we started with. We've seen how Ford-Fulkerson finds the max flow, but what in the world does that have to do with the minimum cut? Well, it turns out, everything. This right here is the max flow min cut theorem. It's the fundamental law we were hinting at. It says these two problems, pushing as much stuff as possible through the network and finding its weakest bottleneck, they're not just related. They have the exact same answer. They are two sides of the same coin. Let's really get the intuition for this, because it's so important. Think about it. Any cut that separates the source from the sink, all the flow has to pass through the edges of that cut, right? So the total flow can never ever be bigger than the total capacity of that cut. The cut is an upper bound. What Ford-Fulkerson does is it finds a flow, and it also implicitly finds a cut where the flow is equal to the cut's capacity. And if the flow can't get any bigger and the cut can't get any smaller, they must both be optimal. The network's strength, its max flow, is literally defined by its greatest weakness, its min cut. Now that we understand this amazing theorem, let's talk about why it's so much more than just some cool theory. This thing is an incredibly versatile, powerful problem-solving tool. It's like a Swiss Army knife for graph problems. The secret is a technique called reduction. The idea is to take a really hard problem, one that might not even look like it's about flow, and you cleverly reframe it as a max flow problem. Then you solve it with something like Ford Fulkerson, and you translate the answer back. Let's look at a couple of classic examples of this. So, for instance, picture this. You're trying to match students to available projects. Or maybe doctors to hospital shifts, or even job applicants to open positions. You have two separate groups, and you want to make as many one-to-one pairings as you possibly can. So technically, this is called maximum bipartite matching, and our goal is just to pick a set of the connections, or edges, where no two edges touch the same person or the same project. We just want to get the biggest number of pairs possible. And here's the brilliant trick for turning this matching problem into a flow problem. We build a new network, we add a source and a sink. We connect the source to everyone in the left group, say, the students, and we connect everyone in the right group, the projects, to the sink. And now, for the most important step, we set the capacity of every single edge in the whole network to 1. Why 1? Well, a capacity of 1 acts like a switch. It means each student can only be used once, and each project can only be used once. It perfectly models our constraint. The total flow you can push through this new network is exactly equal to the maximum number of pairs you can make. It's so cool. Let's take another example. Imagine you're trying to route data packets through a computer network without them interfering with each other. Or maybe you're planning evacuation routes out of a building. You want to find as many paths as possible from point A to point B that are totally independent of each other. Now, we can define this independence in 2 ways. Edge disjoint paths are the simpler kind. They just can't share any of the same roads or connections. Node disjoint paths are even stricter. They can't even share the same intersections or intermediate points. And what's amazing is we can model both of these using max flow. For edge disjoint paths, it's easy. Just like with matching, set every edge capacity to 1. The max flow tells you the number of paths. Simple. But for the harder node disjoint problem, we use another really slick trick. For every node, we split it into 2 tiny nodes, an in node and an out node, and we connect them with a little internal edge that has a capacity of 1. This tiny edge acts like a gatekeeper for the original node, making sure only 1 unit of flow, which represents 1 path, can pass through it. It's this beautiful transformation that lets us model a constraint on the nodes using only edge capacities. Okay, let's bring this all together. Let's talk strategy. How do you absolutely nail this on an exam? To really own this topic for an exam, you need these 4 areas locked down. First, the definitions. You've got to be able to precisely explain what a flow is and what a cut is. Second, the algorithm. You have to explain why that residual graph with its reverse edges is the key to making it all work. Third, the theorem itself. Be able to state it clearly. Max flow equals min cut. That's the main takeaway. And fourth, the technique. Reduction is your secret weapon. Don't just memorize the steps. Understand why setting capacities to 1 works for these problems. And definitely watch out for these common traps. The number 1 mistake is forgetting about the residual graph and those reverse edges. Without them, the algorithm just doesn't work correctly. Second, messing up the capacities when you do a reduction. Just remember, for these kinds of matching or path problems, a capacity of 1 is your best friend. And finally, don't mix up the reduction for node disjoint versus edge disjoint paths. That node splitting trick is what makes the node disjoint version work, so don't forget it. And remember, this is way more than just some abstract topic for an exam. This framework is used to solve real-world problems all over the place. Optimizing supply chains, routing data on the internet, and even in fields you wouldn't expect, like computer vision and airline scheduling. By understanding this one core principle, that a network's maximum throughput is defined by its narrowest bottleneck, you've really gained a new and powerful lens for analyzing the complex systems all around us. So the next time you're stuck in traffic or waiting for a big file to download, you can think about the network, the flow, and the cut. What network will you analyze next?